In this video, we're going to discuss section 3 of chapter 7, polynomial interpolation. And in particular, we're going to focus on Lagrange interpolating polynomials. So another equivalent method to find the interpolating polynomials is the method of Lagrange polynomials. So given n plus 1 data points, as shown here, the Lagrange polynomial of degree n that fits through the data points has this form. So fn of x is equal to L1y1 plus L2y2 plus L3y3 up to Ln plus 1 yn plus 1, which is equal to the sum, as I goes from 1 to n plus 1, of Li yi. Now this Li is defined as shown here, where this is the product operator. So j goes from 1 to n plus 1, where j is not equal to I, because that would make the denominator equal to 0. So it's similar to the summation notation, except that instead of adding, we're multiplying, as we will see in the next slide. So this symbol is used for the product notation. So basically what this means is that for a given I, we want to loop over j using this product notation. So for example, if L3, so I is equal to 3, is equal to x minus x1, so this is where j is equal to 1, divided by xi minus xj, so x3 minus x1. So here j is equal to 1, and then we increment j is equal to 2, and you see that we're multiplying here. So it's the first term multiplied by the second term multiplied by the next term, etc. So again, we have x minus x2 divided by x3 minus x2. And then we skip when j is equal to 3 because I is equal to 3, so this only applies when j is not equal to I. So here j is equal to 4, and then here j is equal to n plus 1. And you can see that I stays the same in all of these because here we're talking about Li. So it's important to note that we skip when I is equal to j in this Lagrange polynomial definition. The Lagrange interpolating polynomials produce the same polynomial as both the general method as well as Newton's interpolating polynomial method, because as we discussed, the interpolating polynomials are unique. So let's revisit the same examples that we used in the previous section for Newton's interpolating polynomials. So here we want to use the Lagrange interpolating polynomials to find the interpolating polynomial to this data of 2 points. So we have 2 data points, so we will create a polynomial of the first degree, or a linear function. So our function has the form shown here, so y is equal to L1y1 plus L2y2, which is and then we can use our product operator to expand out what these L's were. So L1 is equal to x minus x2 divided by x1 minus x2, and L2 is equal to x minus x1 divided by x2 minus x1. If we plug in the values that we have, we see that we get y is equal to 4x minus 3. Now let's add another point and find the interpolating polynomial to this set of 3 points. Here we have 3 points, so we're going to create a polynomial of the second degree. So y is equal to L1y1 plus L2y2 plus L3y3, where we can use, again, our product operator to find all of these L's. And we can plug in the values that we know for all of the values x1, x2, x3. And we see that y is equal to minus 3.5x squared plus 14.5x minus 10. Now we can add another point and use the Lagrange interpolating polynomials to find the polynomial of this data, these 4 points here. So we have 4 data points, so we will create a polynomial of the third degree, which has the form shown here, L1y1 plus L2y2 plus L3y3 plus L4y4. Now using our product notation, the L's are expanded out here, where this is L1, this one is L2, L3, and L4. And if we plug in all of our values for x1, x2, x3, x4, y1, y2, y3, y4, we get the polynomial shown here. And now let's look at the Lagrange interpolating polynomial for these 5 points. Again, we'll add an extra point. So we have 5 data points, so we will create a polynomial of the 4th degree, which has the form L1y1 plus L2y2 plus L3y3 plus L4y4 plus L5y5. So we can use our product operator to expand out all of our L's, and then we can plug in our data points x1 through x5 and y1 through y5, and we get the polynomial shown here. So you can look back at the previous section and see that all of the polynomials that we got for each of the data sets here using the Lagrange method are the same as those that we got using Newton's interpolating polynomials once we expand everything out. And these, again, would be exactly the same as if you used the kind of traditional method, which is setting up the linear system of equations ax equals b and solving for the coefficients that way.